Hello mathematicians, we're now going to take a look at the concept of multiple roots, which is not something entirely unknown to you. You might recall that when we had quadratic equations, we came across the condition on the discriminant for us to have a double root, which was that the discriminant equaled 0. And the fact that we had a double root meant effectively that the quadratic was a perfect square, and the graph came down and it just touched the axis rather than cutting through. Now we're just going to extend on that concept, and to do that we're going to introduce the concept of the derived polynomial. So if we have a polynomial, then the derived polynomial is literally the differential. It's taking the derivative of that polynomial. So the derivative of the polynomial, if we look at it, then the constant term will of course disappear. The derivative of a1x will become a1, a2x squared will be 2a2x, and so on. So the derived polynomial has this general form. Now, the bit that we're interested in is that if the polynomial has a root with a multiplicity of r, so that means that this root has to turn up more than once, otherwise it's just a simple root. And as long as s of a, this thing in here, so when x equals a, this factor is 0. So as long as s of a doesn't also equal 0, then we would say that px has a root a of multiplicity r. If we differentiate, so we get the derived polynomial, then p dashed x will have a root a of multiplicity 1 less, so r minus 1, p double dash has a root of multiplicity r minus 2, and so on. We can keep on going down. Now the proof is worth knowing because I think it illustrates the concept a little bit more. So suppose we had our polynomial, which was the product of this multiple root, which turns up r times, and the rest of the polynomial, left after we divide that multiple root into p of x. Then our derived polynomial will be, by the product rule, we put down the first, differentiate the second, plus put down the second, and differentiate the first. We multiply down by r, we subtract 1 from the power, we multiply by the differential of the brackets, which is just 1. Now if we look at this expression, we can take x minus a to the r minus 1 outside the brackets, which will leave from the first term x minus a s dashed of x, and from the second term r times s of x. Now as soon as we make x equal to a, then this thing out the front is 0. So regardless of what's in the brackets here, that product will equal 0, which means that when x equals a, p of a effectively is 0, which means that we have no remainder, so x equals a is also a root of this particular equation. And we can see that it's a root of multiplicity r minus 1. So, how do we make use of this? Well, it's not some magical routine which is going to let us solve equations easily. It's just one more tool to add to the ones that we already have. So suppose we had this question. We've got to solve this thing, which is a polynomial, over the complex field, given that it has multiple real roots. So we just pick up clues where we can here. So the first thing to do is to notice that the coefficients are real. So if the coefficients are real, it may possibly have integer roots. So we check for those. And if it does have integer roots, they'll be factors of 2, so that will be plus or minus 1 and plus or minus 2. So if we just look quickly, 2 to the 6th is 64, so we're not going to be able to turn that into 0 with x equals 2. But if we look at p of 1, that will equal 0, and so does p of minus 1. So actually x minus 1 and x plus 1 are both factors. Now it may be that they are one or both of those are also multiple roots, but we don't know. But what we do know now is that because they are both factors, then our original polynomial is equal to x minus 1 times x plus 1, which we know is that, times something else, and we can get the something else by doing our long division. So if we divide x squared minus 1 into our original polynomial, and again, you should trace through the working here to make sure that you could do it. But if we do that, we get x to the 4 plus x squared minus 2. So we can write our original polynomial as the product of two factors. Now, if we look at this part, what we can see almost again just by inspection is that if we let x equal 1, then this would equal 0, and if we let x equal minus 1, it would equal 0. So for our second bracket there, the polynomial with highest power of 4, p of 1 is 0 and p of minus 1 is 0. So that means that 1 and minus 1 are roots of x to the 4 plus x squared minus 2, and in fact they are multiple roots, because for x to the 6 minus 3x squared plus 2, it's going to equal at least x minus 1 turning up twice and x plus 1 turning up twice, and then something else. So now knowing this, knowing that they turn up twice, then if we look at what x squared minus 1 squared is, because that's what x minus 1 times x plus 1 is, and we've got that squared, that equals that. If we divide that into our original polynomial, then what we get with our long division is x squared plus 2. So what we can now say is that our original polynomial is x minus 1 squared, so 1 is the root of multiplicity 2, x plus 1 squared, so minus 1 is the root of multiplicity 2, and x squared plus 2. And x squared plus 2 over the complex field is x squared minus 2i squared. So that gives us all of our roots as plus 1, minus 1, minus 1, and I root 2 and minus I root 2. So what you can see is that it didn't really make it quick to find the roots of an equation to the power of 6, but it was just a backup plan, one little fact which we could build upon to help us do what's quite a difficult problem. Now for our next question, find an expression for p of x given that it's monic, which we know means the leading coefficient is 1. It has a degree 4, so it has a highest power of 4. Minus 1 is a single 0, so that's a single root, which means that there's a single factor of x plus 1. And it has 3 as a 0 of multiplicity 3, which means that in the original polynomial, x minus 3 as a factor will turn up 3 times. So our original polynomial is this. And all that remains is for us to actually write that out in polynomial form. So we expand the cube, we have a formula for that, and we'll come across it more later on in the binomial theorem. Multiply through by x and then by 1, and then gather terms together, so this is our polynomial. Now for our next example, show that x minus 3 is a factor of this polynomial. So we know how we'll do that. We can use the remainder theorem. So if we substituted plus 3 into here and we got a remainder of 0, we know it's a polynomial. We know it's a factor, sorry. Or alternatively, we could divide that in and see that it went in with no remainder. Then, hence, using the fact that this equation has a root of multiplicity 2, solve the equation completely. So there are a few bits of terminology to get our head around there, and a pattern to look for. So if the root has a multiplicity of 2, then, on this equation here, given that this equation has a root of multiplicity 2, then we have something that turns up twice, a factor which is squared. We know that the derived polynomial of this will have that same factor turn up once, and when you look at this and this, you can see that this is actually the derived polynomial. And then to solve the equation completely means to find the roots. So let's look at a setup, and this is where I find you really need a plan. So let Q of x, and the reason I pick Q of x is just hopefully something will become apparent. So let Q of x equal the original, so let's do our first task. If it's a factor, then Q of 3 will equal 0, so we show that. So therefore, our polynomial has x minus 3 as a factor. Now, for this polynomial, then Q of x is its derived polynomial. So P of 3 is, we plug those numbers in, and it's 0. So 3 is actually a root of P of x, and it's also a single root of the derived polynomial, so that means it must actually be a double root of Q of x. So x minus 3 must be a double root of P of x, and that means that it multiplied by R of x will equal the original polynomial. So it starts us off on the process of being able to solve it. Now we know that x minus 3 squared is just that, so we now do the division. This into that original polynomial, and again, once we go through the process of long division here, we can see that x squared minus 6x plus 9 goes into our original polynomial, x squared plus x plus 1 times. So that means that our original polynomial, the 1 to the 4th power, was equal to our double root, our root of multiplicity 2, multiplied by this one. And for this one here, its roots are given by the quadratic formula, and they are complex roots. So for P of x equals 0, when we solve it completely, we've got two roots of 3, we've got a double root, and we've got this root and this root, which again, interestingly, appear in or are conjugate pairs. Now, our last example I've just thrown in, and we're going to do this very same example by a different method later on, which I hope you'll find possibly easier than this, but either one is valid. So we have this equation. We're told that it has two equal roots. So it has a double root or it has a root of multiplicity 2. And we have to prove that result. Now that result is definitely not something which is blindingly obvious. So we just apply what we know. So if that polynomial has two equal roots, one of those equal roots must also be a root of the derived polynomial. So we find the derived polynomial, and that's that thing there. 3x squared plus 3h equals 0. So if 3x squared plus 3h equals 0, that implies that x squared plus h equals 0, and x equals, whether you use the quadratic formula or you just shift that across and use complex numbers, x equals plus or minus root h. Now, which one of these roots actually is the double root of this one up here? We have no way of telling. But if we plug them into our original equation, we can see what happens. So if we plug x equals plus I root h into our original equation, which was this, then what that implies is this. So I root h cubed is that. 3h times I root h is that, and of course there's our g. So when we gather terms together, so h root h is of course h to the 3 on 2, so we've got h to the 3 on 2 outside of 3i minus I, which is 2i, and we've got our plus g. So we know that that equals 0. Now if we look at the other case, minus I root h, plug it into this, then minus I cubed becomes I. That's h to the 3 on 2. We've got 3h times minus I root h plus g. Take again h to the 3 on 2 out, and we'll have minus 3i and plus I, so minus 2i, and then plus g. So all that equals 0. Now, if we take each of these in turn, then from number 1, if we shuffle the h term over to the other side, we get this. Square both sides, so g squared, the minus squared becomes plus, the 2i all squared becomes minus 4, and h to the 3 on 2 squared becomes that. Then bring it back, and we've got this conclusion. And here, same thing. So if we take minus 2i times h to the 3 on 2 over the other side, it will become that. Square both sides, and 2i will become minus 4. H cubed, bring it back, we've got that. So whichever way we go, we're proving that relationship there between the g and the h. Now we didn't ever find what the equal roots were, we didn't ever factorise, we were just basically playing with algebra on the basis of some facts that we knew. So in relative terms, this has been a long video and probably a bit slower if you verify these things for yourself. But that's what these questions are like. They are slow, we look for clues where we can, and bear in mind that there are not that many facts to work with, and that we will have a quicker way for some of them later on. So have a go then at these at set 1.